Okay, I think we're ready to start. So tonight, last class of the semester. Next Tuesday is our scheduled final exam period. The final exam period officially starts at 6 o'clock and goes through, I think, 9. But since I'm giving you a slightly different format, I'm going to email or hand out the exam. You have the option of taking it in the classroom here. I'll hand it out. Or if you just want to do it in the privacy of your own home or coffee shop or whatever, you can do that as well. I will either hand out or email the exams at 5, so that you have plenty of time to do this. They will be due at midnight, and I am not kidding, no late exams. I'm going to bed at midnight, and I'm not going to answer my email after that. So get your exams in prior to that time. The exam is open note. Any sort of resource you can find except another human being. No phone a friend, no phone a classmate. And I'm dead serious about that because I can always tell when it happens because everybody makes a mistake. And when you're working with a friend, everybody makes the exact same mistake in the exact same way, and it makes no sense at all. So just don't do it. Don't tempt me. Just don't do it. So do your own work, okay? And that'll be it for the semester. I will try to hand back the homework that you did today by the end of the week. I'll try to get at those tomorrow. I either handed back your homework assignment 1 or emailed you the results earlier today. There was one thing I noticed on homework 1 that I think I should go through because I'm likely to ask a similar question on the final exam. And I want to make sure everybody does it right. Okay, so one of the tasks that you had in homework 1 was figuring out the hydraulic gradient from some well data. The first thing that you have to realize, and most of you did this well, but I had 2 people make mistakes on that, is that you have to use and contour the total head values. I had a couple people use the surface elevation. And what this gives you is the gradient or the slope of the surface of the earth, which some things might be important, but not for groundwater work. You want to contour the total head values. Most of you did this correctly, okay? In order to do it correctly, you have to have a change in your head over a change in your distance, okay? Most of you had no problem finding the change in head. That's simply the distance that it drops, say, from, in this first case, X to Y. Looks like this is maybe 54.5 feet. Y up here looks like 50 feet. Your DH in that case would be 4.5 feet. And then what you have to do is calculate a distance between those, okay? Now the one thing several people did, I'm going to draw this in, let's make it purple because it's incorrect, is they drew a line that might have looked something like that. It's close, but it's not right. To get the maximum gradient, to get the direction that water flows, you want to go perpendicular between all of these gradient lines. So I'm going to draw this in red now. So if you start at this point X right here, what you want to do is you want to take the quickest path and the shortest path, and it would look something like this. And then the DL is the distance from that point right there to that point right there, and you'd have to read that off a map, okay? So that's how you'd figure out the hydraulic gradient. Now this second case over here, you can see that the lines don't parallel one another. And that's fairly common in real world scenarios. So what you need to do is you need to go the shortest distance, and that's going to change between each line. So you can see that the path is somewhat curved as you go through this. You want to take the length of this curved line right here. Okay? So always do, let's say if you're starting right here, this X, your flow path would look something like that. It would curve off. That's the shortest distance between those lines. Okay? So for calculating the hydraulic gradient, that's how you do it. Calculate the drop, which most people did very well. Calculate the distance, which you can read off your map. Make sure you follow the maximum gradient, which is the shortest distance between those contour lines. And again, you're using total head values, not surface values. Okay? Do you guys have any questions on this? All right, let's get on to our last topic for the semester. I don't know how long this will take. I don't suspect it'll take the entire class period, but we'll see. All right, last topic of the semester, something called capture zones. This is kind of a big topic in groundwater, both in rural areas and in urban areas. And specifically, we are going to today look at the capture zone for an unconfined, which we've also this semester been calling water table, aquifers. These again are aquifers that are not protected by a confining layer. And because they're not protected by a confining layer, they are very susceptible to contamination from surface sources. All right, I'm going to start out with about the simplest case that I can think of. So this is an unconfined aquifer with a hydraulic gradient, dH over dL, of 0. If your hydraulic gradient is 0, what does that mean? What does that tell you about the water table? Horizontal, right? Totally horizontal. So let's sort of draw this, all right? I'm going to draw green for the ground surface. All right? We're going to stick a well in there. Let's put a well down. This light blue dashed line is the water table before pumping. Now, when we start pumping, what happens to the shape of the water table? If we pump at a greater rate than can be recharged, you should get a cone of depression, okay? So I'm just going to draw a cone of depression here in purple dashed line. I'll fill it in to make it a little bit more noticeable. All right, there's our cone of depression. Make the well a little longer here. Okay. All right, so let me use red right here. What about right here? This red blob I just drew. Is that getting sucked into the cone of depression right now? It's not part of the cone of depression, is it? Or if I went over here, this isn't part of the cone of depression. There's no change in the gradient, right? So there's no reason for that water to move. It's just going to stay stagnant, okay? So this cone of depression is going to suck in water from kind of this area here. So this is sort of the boundary of the cone of depression, right? If we look down on this from above, a map view, which let me sort of draw this over here. So now we're looking down on the area. Here's our well in the middle. What's the outline of our cone of depression going to look like? Remember, this is a three-dimensional problem, right? On the left, I drew just a two-dimensional version. Three-dimensional, you just sort of spin it all the way around, right? So if you look down, what would your cone of depression look like from above? The area that includes the cone of depression. You guys following what I'm asking? So if these lines right here represent sort of the outer limit of the cone of depression, what would that outer limit look like if I look down from above? Be a circle, like right around like that, okay? So it would be lowest here in the middle, and then when you're outside of that red line, this area out in here, you're outside the cone of depression. This area inside, right here, that is called the capture zone. What that means is that you want to be very careful with what activities go on right above that cone of depression, because the water is going to get sucked into the well, right? You don't want a pig farm inside of this red line. Or if you're in a city, you don't want a chemical plant inside that red line. You don't want any activities that could leak into the aquifer and damage the water. You don't want a gas station in there. If you're out in rural areas, you don't want to mix herbicides and pesticides in there. This is a big issue in rural areas because you've got farmers and ranchers, they have crops, they have livestock, and they're going to back their trucks up to these wells, get water for their pesticides, herbicides, or whatever they're going to use for their cattle. And a lot of them used to mix their chemicals right next to the well. And inevitably, some of it would spill, and you end up with herbicides and pesticides in your well water. And a lot of ranchers and farmers also use this well for their own personal drinking and living. So there was a big push about 20 years to educate farmers and ranchers and say, you know, you can't do these sorts of activities right by your well, because you're going to pollute it, and then ultimately you're going to pay the price by having polluted water. You need to grab the water and then drive some distance away so that you can mix these chemicals and do things safely. Well, the thing is that the farmers and ranchers and everybody else didn't know how big this circle defining the capture zone was. This is something that hydrologists have to figure out, okay? Do you have any idea or any ideas on how we might calculate the size of that capture zone from things that we've done already this semester? So obviously this is pumping, right? Pumping creates a cone of depression. Last week, I gave you some pumping equations, right? Take a look at the pumping equations from last week and see if you can come up with a way for us to calculate how big to make that capture zone based on the rate of pumping and the hydrologic properties of the rocks and water. So just take a minute and take a look at that equation, and can you think of a way to use it for this? Okay, so I put the equation from last week up here. So this is for pumping, creating a cone of depression. Okay, if you're pumping, you're always going to have Q, right? You're always going to have a value there. 4 is a value that's always there. Pi is a value that's always there. T is transmissivity. So you're always going to have a value there, right? And then you have this W sub U that you looked up from that table. Over on the left side is the drawdown. Where do you have the maximum drawdown when you're pumping a well? It's right at the well, right? That's the lowest part. And then as you move away, as R increases, the drawdown gets less and less and less. What's your capture zone? Capture zone is where what? Looking at this equation. How can you define the capture zone based on the equation here? What's that? Yeah, so R, but R varies, right? You can be real close to the well and it's a small R, and as you move away, you get a bigger and bigger R, right? You want R where? And what's the very end? Okay, and in this equation, where does the cone of depression start? How would you define the edge of the cone of depression? You're exactly on the right track. What's the drawdown when the cone of depression ends? 0. So when this is 0, that should tell you ultimately what your R is if you work through it, right? No. Sadly, remember these are mathematical models. That's completely the right thinking. The problem is that if you look at your chart, so in order for this to be 0, what does this term have to be? Because this is always going to be a value, right? It's always going to be some number. Some number multiplied by what gives you 0? 0. This has to be 0. If you look at your table, W sub u is undefined for values of 0. It doesn't work, sadly. It would be great if it did. This would be an easy way to calculate a capture zone. It gets close and close, it's an asymptote. It gets close and close, but never quite gets to 0. Again, it's a mathematical model. So what that means is we need new math, sadly, to calculate a capture zone. Now the other thing is it's really rare to have a water table that doesn't have a gradient. It's pretty unusual to see a perfectly horizontal water table. Usually the water's flowing one direction or another, okay? When you do that, when you have water flowing a certain direction, it changes the shape of your cone of depression. So let me go on to this next page and show that to you. Let's say we have a surface that looks like this. What's the groundwater table likely to look like in this area? It tends to mimic the ground surface, right? So let's draw in our suspected water table. Which direction is the groundwater going to flow? Always flows downhill. So the water's going to flow this direction. Now let's put a well in. What do you think your cone of depression is going to look like when you have water flowing like this? Is it going to be perfectly symmetrical on both sides of the well? No, in fact, what it's going to look like, I'll draw this in purple, is it's going to go maybe something like this, and then something like that. So you're going to have an asymmetrical cone of depression. Okay? All right, there's your well. What's your cone of depression going to look like from above, or the capture zone? In the last case, it was kind of a bullseye, right? What's it going to look like in this case? Okay, and let me add this in. So let's just say the water is flowing in that direction. What do you think capture zone is going to look like? (2D to 3D) is always challenging, but give it a shot. What do you think? It would be more like an oval, right? In fact, yeah, it would look like, you can see how close that edge is there, right? And then this edge is pretty far away. So it might look something like that. So this would be the capture zone for an unconfined aquifer with a hydraulic gradient, dH over dL, that's greater than 0. Okay, let me give you an example of how hydrologists can deal with this mathematically. I'm just going to work through this. I'm not going to actually give you one of these problems on the final next week. I'm just going to go through it in class so that you sort of see how the math works. The reality is that the pumping equation that we used last week was just one of dozens. And you have to make and use different equations for different groundwater scenarios. If you ever go out and actually work in groundwater, you don't do a lot of this by hand. All of it's now software based. There's programs called, there's one program called ModFlow, where you basically type in all of your aquifer characteristics, water characteristics, hydraulic gradient, and it will tell you about the cone of depression that is created by those conditions. And it has different setups, whether you're dealing with confined aquifers, unconfined, leaky confined, and fracture flow, Darcy's flow, all sorts of different possibilities. So that's why I'm not going to go through 50 different equations in this class, because in reality, if you ever do this kind of work, you're probably going to be doing it by computer. And the thing I want you to realize is that these are just mathematical models. They're not perfect. Your model has to mimic the actual conditions as best as possible. And for some situations, like the one I just talked about, sometimes they're not defined for that. You know, in the case of the pumping equation we used last week, it's not defined for areas where there's no drawdown. It only works if there's a drawdown. So we can't use it to define a capture zone. So we come up with different equations for different scenarios, and we can come up with equations for figuring out these capture zones as well. So what I want to do is give you a little scenario here. Let me redo that. Let me make it a little bigger. All right, so let's say we have a well right there. Let's say our groundwater movement is that direction. Let's say that right there is a landfill. This right here is a proposed city well. So you have a growing city, they need water for its citizens. The question here would be, could the landfill pollute the proposed city well? If it can, then you don't want to put the well there, obviously. You'd want to look for a different site. So if you calculate the capture zone, and it looks something like this, where everything within this area right here would ultimately flow into the well, do you have to worry about the landfill? No. That would be good. But what if the Capture zone looks something like that. Then you have a problem, right? The whole idea behind these capture zones is delineate an area above the water table that could impact the groundwater flowing to a well. And then you can use that for intelligent zoning. You know, the city could say, we're not going to let people put a landfill in there. We're not going to let anybody put a pig farm in there. We're not going to put a new subdivision in there. Okay? So how do we actually figure out the size of these capture zones? Well, let's sort of think about this realistically. What is the size of a capture zone dependent upon? You can probably think of a few factors that would play into it, and maybe not some other ones. What sorts of things can you think of?
Radius.
So, radius of the capture zone?
Yeah.
How do, okay, so, no, that's, okay, so let's say you have this, let me draw this. Let's say you have this well right here. You have water flowing this direction. What if you just pumped a little bit? What if you just pumped a tiny bit of water out of there? Would you have a big capture zone or a little capture zone? Be pretty small, right? You might have a capture zone that's that big. What if you pumped a lot? You might have a big giant capture zone, right? So we know right from the start that the capture zone is going to be dependent on the amount of pumping. So pumping rate, which we measure in cubic meters per second or cubic feet per second. What else would affect the size and shape of the capture zone? What's that? Recharge, okay? The more it recharges, the smaller your zone is going to be because there's more water getting into it. What else? Okay, type of rock. You're definitely on the right track. So what about the rock? What if it was, let's just start with porous, okay? What if it was really low porosity versus really high porosity? How would the shape change just based on that? If it was high porosity, how would it look different than something that was low porosity, do you think?
If it were higher porosity, then essentially more water can flow into the cone of depression. There's just more speed that can move into it.
Right, there's more water close to the well, right? So the capture zone wouldn't be as big, right? If you have very little porosity, which means very little water, then it's got to drag water from a really great distance in, right? So the aquifer characteristics. Porosity. Another one is thickness. If you have a really thick aquifer, it can hold more water. And your capture zone should be smaller. One thing we've already talked about, I guess we can put hydraulic conductivity, which kind of encapsulates a lot of the aquifer characteristics here. How easy is it for water to flow through? One we already talked about is the hydraulic gradient. Remember, if the gradient is steeper, water flows faster. If it's very shallow, it might look more circular. If it's very steep, it's going to be much more oblong. And then usually we do capture zones over a time, say 5 years, maybe 25 years. Yikes, what is that? Like, how far would the water have to move to keep filling this over a 25-year period versus a 5-year? If it's just a day, it's not going to take in much water, right? The capture zone is not going to be very big if you're only worried about, oh, how much water is going to be captured in a day. Might be very near the well. But if you want to know, oh, we need to protect this for 25 years, then it might be something that is totally different. Okay, so let me just give you a set of equations. And again, I'm not going to make you do this on the final. I just want to sort of illustrate it in case you ever come across this. If you ever work in groundwater, you are likely to come across this. So here's how you would compute the capture zone for a, let's say in this case, a confined aquifer. We typically do it for unconfined, but we can do it for confined aquifers as well, because you can pollute a confined aquifer. It's a lot harder. But the reality is that if you're a city looking for water, you're going to try to find a confined aquifer because you know it's going to be safer. But then you also want to protect it as well. So there's actually 4 parts. Whoa, change color on me. And I need to draw a little diagram here to illustrate all the different things that we're going to look at. So right here in the middle of our XY diagram, that's going to be your well, okay? This is your Y-axis, this is your X-axis. And then this is our capture zone. I'll redraw this. Let's see. So right here, you can see that the shape of these things, it sort of gets to a certain width and then doesn't get much wider. So this distance here from the well to the maximum width of the capture zone, this is called plus Y max, and this will be minus Y max. This distance right here, from here to here, is your X max, so it tells you just how far up gradient your capture zone goes. And this point right here is X naught, which some hydrologists also call a stagnation point. So we want to calculate several different things. We want to calculate the stagnation point. We want to calculate Y max. It might be nice, in order to get the shape here, to have some intermediate points kind of along the way before it hits its Y max. So the intermediate points sort of define the shape of this little snout on the end of it. So we need some intermediate y points. And then finally, we need x max. And if you have all of those, you can define the total shape of your capture zone. Now this varies, again, these equations will vary depending on whether it's a confined aquifer, a leaky confined aquifer, an unconfined aquifer. So there'll be slightly different equations for both. I've just picked this one actually because it's the easiest of the bunch. The other ones get a little more advanced, but they're not terrible. So I'm just going to put the equations down, and then it's just sort of plug and chug. So these have been derived mostly empirically, which means through trial and error. So again, I'm not going to ask you this on the final. I'm just going to work through this now so that you've seen this at some point. So again, x naught is the stagnation point. And it equals, and I'm just going to draw this out here, negative q over 2 pi k, let me write that a little better, b dH over dl. So that's going to give you the value for x naught, which is right there. And if you look, that's going to be a negative number, isn't it? It's going to be a negative x value. If you just assume that the well is at 0, 0 in this xy plot. And if you look at the equation, negative q will give you a negative number. X max is plus and minus q over 2kb dH over dl. Intermediate points, x equals negative y over the tangent of this big quantity here. 2 pi, it's like a alphabet soup here. kb dH over dly over q. Looks complicated, but then again, it's really not too bad. Draw this a little better here. And in this case, you have to put your calculation in radians rather than degrees for it to work out. And x max equals T times V, where V equals negative K over N, which is the porosity, dH over dl. So with those equations, you can define all the different points. And I'll just go through a problem. It looks terrible, I think. I'm guessing to you this looks terrible. It's actually not that difficult. We'll do a problem. We can work through it in a couple minutes. All right. I'm not even going to ask you if you have questions, because I know you do, or you don't even know what questions to ask at this point. So let's just go through a problem, and hopefully that will kind of show how to use this equation. And again, in real life, you'd punch this into a computer program. But I want you to sort of see what these computer programs are based on. So compute the capture zone for a well, pumping at a rate I've got a button or something that keeps changing my color. Of 190,000 cubic feet per day. So this would be something like a big municipal well for a city. They're going to be sucking out a lot of water. And they're sucking it out from a confined aquifer. So we can use the equations that I just put up because it fits the situation that we have here. With a thickness of 75 feet. A hydraulic gradient 0.003 and a hydraulic conductivity of 1,500 feet per day. Your porosity is 0.1, something like a sandstone, 10% porosity, and we're doing this over a period of 5 years. Okay? So this is the question's pretty straightforward. You have a well, it's pumping at a certain rate, pretty high rate actually. Your aquifer is 75 feet thick, it has a porosity of 0.1, it has a slope of the water table or the potentiometric surface of 0.003, and it has a hydraulic conductivity value of 1,500 feet per day. That kind of is a measure of how easily the water is moving through it. So you've got pumping rate, you've got aquifer thickness, you've got aquifer properties, and you have the time. And that's pretty much all you need to do these equations. So I'll just go through this. So part one, x naught, which is the stagnation point. So how far down gradient does your capture zone go? Well, going back to the equation I gave you on the previous page, negative q over 2 pi k b dhdl. I've given you all these values. (1,900 cubic feet per day) over 2 times pi 3.14 times your hydraulic conductivity, which is 1,500 cubic feet per day, times your aquifer thickness B, which is 75 feet, times your hydraulic gradient, 0.003, which is a dimensionless value. I have one wrong value. That's not feet cubed, it's just feet per day on that. Okay, so let's see what we have. So we have feet, feet, feet squared. Cancel that out. plug through the math, and you would end up with a value of 89.6 feet. So that means, if we go back to our little diagram, if this is the well right here, and if your capture zone is looking like this, that means that that point right there, x naught, is 89.6 feet from the well. Almost 100 feet, 30 yards. So anything farther away than that, you wouldn't have to worry about messing up your capture zone. So that immediately defines the size, kind of the snout or the end of the capture zone. Part 2, which is Y max, kind of the widest part of the capture zone. It's plus and minus Q over 2KB DH/DL, which equals plus minus 190,000 cubic feet per day over 2 times 1,500 feet per day times 75 feet times 0.003 feet cancel, days cancel, and you end up with plus and minus 281 feet. So again, if we go back to our, so this was x naught, the stagnation point was 89.6 feet from the well. And then the maximum width of this thing is 281 feet in one direction and 281 feet in the other. So basically a football field wide. So your capture zone is going to look something like that. What we don't know yet is just how far this way it goes. That's going to be x max, which is what we'll calculate forth. And we don't know the shape of the front of this. We don't know whether it looks like this or if it looks like that or if it looks like this. So that's why we'd have some of these intermediate points. So that's what the next set of equations does. So part 3 are the intermediate points. This is probably the most difficult one to deal with because it's got x and y in here. So I'll just put up the equation again. So what you end up doing for this is you plug in values for y that are between 0, which is on the y-axis, and y max. So remember, we have our stagnation point, we have our plus and minus y max. This was 281 feet. This was negative 281. This was negative 89.6, all in feet. And now what we do is we simply chug in values for y, okay? So remember, y is going up and down on the axis, so we could put in y equals 100 feet, which would be maybe plus or minus 100 feet, which is maybe right there. So where is x going to be? And then we could do that for y equals plus minus 200 feet. And then we could do y equals plus minus 250 feet. You can do as many of these intermediate points as you want. A computer would do every intermediate point and give you a nice perfect curve. But if you plug in the values, if you plug in y equals plus or minus 250 feet, you end up with an x of 682 feet. If you plug in y plus or minus 200 feet, you get an x value that equals 156 feet. If you plug in a y value that's 100 feet, chug through the equation, you get an x value that's negative 48.9. So what it's saying is that when y is, let's say, 100 right here, plus or minus 100, your x value will be over here, negative. When y is at 200 feet, let's say right there, your x value is 156 feet, so it would be somewhere over here. When y is at 250 feet, it's going to be maybe right there, and right there it's going to be 600 feet this direction. So what that gives you then is sort of a perfect shape. I kind of missed the dots there, but you get the point. So it allows you to get the perfect shape of that front curve. You have your y max, you have your x max, or stagnation point, you have some intermediate points, and then finally your x max equals velocity times time. K dh or dl over n equals 1,500 feet per day times 0.003 I forgot to put times time here, sorry about that, over n, 0.1 times time. Our time is 5 years, but we have days here, years here, so we need to convert and change this to days, 365 days in 1 year. Calculate that through, you get an x max of 82,125 feet. If you divide by 5280 feet per mile, this ends up being about 16 miles. So what that means, ultimately, is that if this is your well, your cone of depression would look, your capture zone would look something. Let me do this a little neater. That's terrible. Ugh. All right, let's draw this a little better. Or not. Your cone of depression capture zone would look something like this. where it goes that way 16 miles. The front of it's 89.6 feet in front of the well. The maximum width here is about 281 feet. And you can divine the whole shape just from those simple equations. Again, mostly do this with computer, but you at least see where the math is going with this. Now, if you have a leaky confined aquifer, you have slightly different equations. If you have an unconfined aquifer, you have slightly different equations. But they're all based on the same principles. So the bottom line is you can nicely create the shape of the capture zone, and then you can look on your map and say, oh, is there anything within that capture zone that could threaten the water quality of my well? And if there is, then maybe you don't want to put the well there, or maybe you know, if somebody's got a pig farm, you, as a city, you buy out the pig farm, remove the pigs, and clean up the area before you put the well in. If you're a rancher, you just make sure that you don't do anything within that capture zone that could threaten the water quality of your well. So again, these capture zones are a big deal. Big deal in hydrology, big deal for cities, big deal for agricultural areas, and it's all about protecting groundwater from surface activities by defining the size of the capture zone. Make sense? And again, I'm not going to make you calculate this on the final, but you at least have a workup in your notes should you ever have to take a look at how this all works. Do you guys have any questions? That is all I have for you this semester. So, get your second homework assignment in tonight. I know most of you have been working hard. I've seen more than half the class today working on their cross sections. So I think most of you have figured out how to do that. Get that in, and then it's just the final next week. If you have any issues between now and the final, you can email me. If you have questions during the final and you're not here, you can email me or call me. I'll probably put my phone number on the exam, and I'll take your calls during the exam. I'm going to be sitting right here if you have questions. I don't know if any of you will show up to class. You don't have to. You can take it at home if you want, but I'll be here. Sadly, till midnight if I must be. So it's all right. It's the last class of the semester. We must suffer, right? Okay. Have a great week, and I will see you guys, or maybe I won't see you guys, but I will hear from you guys next week.